First of all, it's a great pleasure to be here, and I must say I was influenced by Maxim many times during my life, and what I will be talking about today is actually a joint work in progress with Maxim and Jan Soibelman. So let me start with writing the title, and then somehow getting myself out of trouble with the title. Algebra of the infrared and secondary polytopes. Secondary so it is a joint work with Maxim and Jan Soibelman. So first of all, it may be a little unusual for mathematicians, the term algebra of the infrared. It was borrowed from the title of the work of Gayotta, Moore, and Witten of this title. So I will not start with this. I'll just say that the term comes from this work. I'll explain a little bit later. And now let me do like the most elementary logical exposition, which will start with secondary polytopes and their properties. And then turns out that some of the properties are relevant for this physical point of view. So let me start maybe here, call it reminder on secondary polytopes. Would be probably part one, secondary polytopes. So this is a concept that was introduced in my joint work with Gelfand and Zelevinsky way back in the 90s. With the goal of studying discriminants of polynomials and many variables. So I recall the context, and then I recall the main setting, and recall what was the old point of view on this setting, and what somehow is the new source of examples for this setting. So we start with a finite set of points in Euclidean space. So in the old setting, it was really a point. The set consisted of points with integer coordinates. Is the set of monomials. We interpret integer point as a Laurent monomial. And then we consider the space of polynomials over those monomials and look for those polynomials that define singular algebraic hypersurfaces. But this construction makes sense for any subset of points in Euclidean space, integer or not. So we imagine something like this. So a bunch of points. We'll take their convex hull. Then some of the points are inside the convex hull. Some points are vertices of the convex hull. Let's call it Q. It's a convex hull of A. Some convex polytope. And we're looking at triangulations of this polytope into simplices with vertices in A. Something like this. Something maybe like this. And maybe there are some other points of A which are not being used in the triangulations. So let me move it up. I'll just right here. We consider the totality of okay, all right. Triangulations. triangulations, let's call them T of Q, into straight simplices with vertices in A. Now, inside this set, it's a finite set because we fixed the finite set of possible vertices. Inside, there are so-called regular triangulations. Is those which possess a piecewise convex function with respect to this triangulation, which is actually strictly convex in the sense that actually breaks down on every intermediate face, regular triangulations. Those exist, strictly convex. T, piecewise linear function.
But you allow it to be constant on one face, yeah?
Yes, it may be constant, it might be linear, so yes. So, and the secondary polytope is a polytope in the space, or let me write it here. So sigma of A, this is the secondary polytope. It lies in the space of functions on A, which means R to the A. It's a polytope, again convex, of dimension equals cardinality of A minus D minus 1, whose vertices are in bijection with this type of triangulations. In general, it is strict inclusion. So vertices, I call them, let's say phi t called regular triangulations. So it's not a definition, it's a reminder, yes. So it can be, this is a certain particular function. So this is a function from A to R, I can write it. Phi t is a function from A to R, and phi t of a point W is the sum of the volumes of the simplices of the star of the point W in the triangulation, equals volume of star of W. That's the definition, and the theorem is that all those points are actually vertices of some convex polytope, which a priori it's not clear why they are.
Just a second. Can one measure volume not with respect to Euclidean measure, but some kind of non-constant density?
It's possible, but this has not been studied. In particular, it's an interesting direction is the hyperbolic case, in which case it's very close to the Penner's construction of triangulation.
You define this convex set by the function. So because you have the same notation for function and for convex set. I'm confused.
No, so it's a function on the finite set. So it's A is a finite set. So we consider a function, so you can Euclidean space of dimension equal to the cardinality of A.
So you define a convex function or convex set?
No, I define a vector. It's a
vertices of polyhedra.
No, vertices of sigma of A.
Elements of R functions on A.
Yes, so the polytope is in the space of functions on A. Okay. So each vertex is an individual function on A. To each triangulation, we can associate an individual function, which to every point associates the volume of the star of this point.
It's a mysterious definition.
It is mysterious, yes. Yes, so I'll say a little more so in the reminder. So an example of this, and
again, but the object is a polytope, right?
The object is a polytope, yes.
But you define function. I'm confused.
I defined what will be a vertex of the polytope.
I define vertex of polytope.
Individual vertex is individual this thing. So altogether, they form the set of vertices.
Consider all these functions with point to all stars.
Yes, to all triangulations. All triangulations, yes.
Yeah. So you define the set, and then you say convex function.
Yes.
But you don't know a priori it's convex or not?
A priori it's a theorem that all those points are in the convex position. It's a theorem.
Okay.
So consider an example. Suppose A itself is a set in the plane. So D equals to, and this is in convex position. or A itself in the convex position. Means it's something like this. So all the points are here, right? We label them, say 0, 1, 2, n, right? Then a triangulation is the same as a bracketing of symbols. So if, for instance, I write here, say, A1, I write A2, here I write AN. So here I write some bracketing. This will write A1, A2. For instance, this is 3. So it would be, this is 4. So this would be A3, A4. This would be the bracketing like this. A3, A4. And so on. So here would be bracketing. So in this case, sigma of A is the so-called Stashev polytope, or assohedron. So vertices are bracketings of A1, AN. And those polytopes are, of course, very classical, very well known. And what's important, let's call it polytope K n plus 1, Kn, that they form an operad, which means every face of assohedron is a product of other assohedra. Let me write it here.
Can you say why this dimension? Why so low dimension?
So this is the space. This corresponds for global affine linear functions.
Now maybe I just explain something to me without formulas. You consider functions on set A, all real functions, and you get kind of low convex hull.
Yes, yes.
And you can then give different piecewise symmetric composition. You get on space of linear function, you get some fan. It kind of dual polytope to this fan.
Yes.
That's it.
Yes, yes. So every face, so we have maps like this: K n cross K A1 cross K AN is embedded as a face into K A1 plus AN. So this is a structure of an operad. So what happens in general is that the arbitrary secondary polytope also has this type of structure. So every face is a product of other secondary polytopes, just like here. So let me call this the factorization property. It says that every face of sigma of A is a product of other secondary polytopes, of other sigma of some AI. More precisely, one can describe what the faces are. So then, indeed, it's probably better to say use the convex hull construction, as Maxime pointed out. Let me get it here. So this goes down.
All three actually move.
Yes, but I'm afraid that with the third one, I'll paint myself into a corner. I won't know what to do with it. Yeah, no? Okay.
You can make any permutation.
Okay. Okay, maybe I'll use it next time. Yeah. Yes. So what really happens is that faces, they correspond. Well, if vertices correspond to triangulations, that faces correspond to something in between, which is subdivision, but not necessarily into simplices. So faces FP correspond to, again, regular in this sense, regular polyhedral subdivisions. It's called P, which says they represent Q as the union of some subpolytopes Qi, or something like this, for instance. So like suppose we have this point here, and this we subdivided our hexagon into 3 quadrilaterals. Yes, to be completely precise, we need this plus a choice of a subset AI in A containing the vertices, such that Qi is the convex hull of AI. So strictly speaking, there is some freedom here. So, and the corresponding phase, Fp, is simply product of sigma of AI. There is a particular choice. So we can, for instance, ask, why don't we put AI to be Qi intersected with A? We can do this, but in this way, we don't get all the faces. So and let's call this the geometric faces. They're also interesting, so-called geometric faces. So anyway, we have this kind of self-referential factorizing structure, that every face of the polytope is a product of similar polytopes, which is something like the operatic structure, but really is a little more general. And one has to understand it in some other way. So now let me do an equally elementary reminder about Lie algebras and L-infinity algebras. So if we have, I recall it, we have a G Lie algebra, then to this we associate its cochain complex, which is exterior algebra of G, with the differential, which is a commutative DG algebra. So in more general, a Lie infinity algebra is sort of a derived analog of a Lie algebra. So it's something like a complex. Yes, dual, yes, of course. Yes. Yeah, with the differential and with bracketing, which is only satisfies Jacobi identity up to the next bracketing. So there is a differential D, which we consider as operation of order 1. We have bracketing from G, tensor G, to G, which consider operation of order 2, but Jacobi up to Jacobi up to lambda 3 from G cube to G and so on. And this is encoded, again, is very familiar, by differential in the symmetric algebra of the dual space to G and shifted by 1. And some differential, let's call it D, satisfying that D square equals 0. So one identity, D square equals 0, it contains in itself the fact that this is 0, that the Jacobiator of this is the boundary of this. Minus 1. Oh, no, that actually I could never remember, yes. So it goes, for instance, if you look into this, G star goes into, well, first of all, is G star of minus 1. That's the differential, that is lambda 1. It goes to S2 of G star of minus 1, which is in the more familiar notation. It's sort of lambda 2 of G star shifted by minus 2. So that's the bracket, that's the dual to the bracket. So then the next would be lambda 3, and so on. So from this point of view, this one condition is a sequence of this recursive conditions going forever. And it includes, it contains the Jacobi identity.
Do you have a strong reason for setting lambda 0 to 0?
What is lambda 0? Is the curvature?
It would be. No, yeah, but it would. But also, it's the constant term in D.
So in those applications, this so far was not necessary. But maybe later.
That's the answer to my question.
Yes, maybe later it will be. Okay, so now if I do a permutation, so this goes up. And the two of those go down. So this is a permutation. Okay. So now let me go to part 3 to combine those two observations. And let me call it the chain complexes of the secondary polytope chain. Or let's say of secondary polytopes in general. So I keep this notation. If I have any convex polytope whatsoever, any. Well, let's consider the most naive cellular chain complex called C of P. So it's just the dimensions of the chains, of the I chains, is the number of faces. So I can write it like this, direct sum over F being faces. And here, well, strictly speaking, the corresponding summand is not is this orientation space. So let's say we work over a field K. So here we have orientation space of F, and simply shift by dimension of F. That's orientation space.
You notice F because F capital and
Yes, over all faces. Yes, all faces, which is just the most naive thing that is studied in the elementary courses of combinatorial topology. Right? And so this means in degree minus the dimension of F. So in here, of course, the differential squared equals 0. Right? So now let's apply this to the secondary polytope and apply the information about the structure of faces. So apply to P equals sigma of A. So what really happens is that the differential takes a face into sum of all of its subfaces of codimension 1. But subfaces are products of other secondary polytopes. So we have some kind of multiplicative structure. So it looks like a differential in an algebra. So, and let's do this. So let's form a vector space V to be direct sum over all A prime of those subspaces VA prime, and this is simply VI prime is simply this. Is orientation of sigma of A prime shifted by dimension. Huh? No, yes, otherwise it sort of collapses, yes, cardinality of A prime. D plus A, yeah. So this is a vector space. And let's form a symmetric algebra of this vector space. So form the symmetric algebra. So and with this operation, call it dot. So my claim is that the factorization property of the secondary polytopes implies that this algebra acquires a differential, an algebra differential, satisfying d squared equals 0. So let me first state it as a claim, the factorization property. Gives a canonical differential. Algebra differential in symmetric algebra of V, satisfying a differential D, satisfying d squared equals 0. So basically, it is unraveling of these definitions. Let me explain what happens on generators.
You mean algebra derivation, which?
Yes, yes, it means satisfying the Leibniz rule. Yes, yes. So, as usual, such a derivation can be described on generators. So maybe I'll do it here. On generator, say V A prime. And here I'm going to use the chain complex of the secondary polytope of A prime. So use chain complex of...
Even who is who, I mean, just forgetting notation, we keep saying glad to say, keep forgetting who is who.
Ah, okay. So, so sigma of A prime is the secondary polytope. V is just one-dimensional space which is associated to this. The summand in the chain complex. So I want sort of to combine them all together. So the chain complex of individual polytope is a finite dimensional thing. But because of the kind of regularity present in this factorization property, they can be combined together into differential and infinite dimensional algebra. So the algebra itself is infinite dimensional. Yeah, so it will be finitely generated. Yeah? So we use the chain complex of the secondary polytope. So look at faces of sigma of A prime. They correspond to subdivisions, FP prime, subdivisions, yeah, into some, let's say, Q second I, A second I. So what happens is this, the part of the differential of the chain complex of the secondary polytope goes into, from VI, VA prime, to the symmetric product of VA second I. So in this, we take this, take differential on VA prime to be sum of those for all faces of codimension 1. Sum of this for all codimension 1 faces. So we sort of patch together. For every generator, we consider its own secondary polytope and use a piece of its chain complex. And then because in the setting, it is clear that d square equals 0 just because for every polytope, d square equals 0. So now, equivalently, it means that just from nothing, just from a bunch of secondary polytopes, we produced a Lie infinity algebra. How should I put it like this? No. Okay, this goes here. This goes here. Yes. So what we have a differential in the symmetric algebra of a vector space, which means that appropriately dual and shifted vector space becomes a Lie infinity algebra. So equivalently, let's call this vector space G. It is the dual space to my space of generators, right there, V star shifted by 1. Again, it's a direct sum over subsets A prime in A, cardinality of A prime greater than D plus 1. And here I have the orientation space. It can be dualized, not dualized. It's identified with its dual. Here I write -1 minus dimension sigma of A prime. So is a Lie infinity algebra.
Again, it should be shifted by -1. Okay, so
If one that was by -1. Oh, okay. Yes. You're right. No, could never. So just from nothing, we had produced certain Lie-infinity algebra. And we sort of can understand, by looking at what happens here, what are faces of codimension 1, what is the nature of operations in this Lie-infinity algebra. So lambda n, the nth n-linear operation, is approximately operation of gluing together, is the operation of gluing together n sub-polytopes in a subdivision corresponding to a face of codimension 1. And let's call this in a coarse subdivision. So if triangulations are vertices and arbitrary faces are subdivisions, that faces of codimension 1 are sort of minimal subdivisions, which you cannot do less than that. And let's call them coarse. So what are examples of this? So for instance, if we dissect our polytope into two parts by hyperplane into A and B, then it gives me the binary bracket, which simply says that AB is the whole thing.
Do you have lambda 1 as well?
Lambda 1 is the differential. So a priori, in this setting, we would have it. It would correspond to a subdivision which are differential of this. It would be sum over inserting of all the internal points. Yes, a priori, there will be a differential here. Yes. Again, if we restrict to geometric faces where this freedom is removed, then the differential will be 0. So, but it is not, this is by no means the only operation. So for instance, it will be example number 1. Example number 2, if you subdivide something like this. If there is like 3 parts, A, B, and C, then the lambda 3 of A, B, C would be the whole thing. And in general, in higher dimensions, there are many more possibilities for doing this. So there exist more examples. So it's sort of geometric way of gluing together, geometric way of formulating gluing together polytopes. Yes, algebraic, yes. Gluing together is geometric, and this is algebraic, yes. Right. Yes, maybe, yeah. No, I can say this too. Yeah. So let me just say that this Lie-infinity algebra is nilpotent, because clearly there is a limit on how far we can go. It's a nilpotent Lie-infinity algebra. So let me now describe a version of this. Once we sort of get into the hang of this construction, then we can think, OK, so now we took chain complex. Let's take chain complex with coefficients. There are not only homology with constant coefficients. There are homology with coefficients in a sheaf. So how we construct something where coefficients will be present? And this actually is an interesting question. So let me explain this in the case will be most interesting for us is the case of 2 dimensions. Let me call this part versions with coefficients. Version with coefficients. In 2 dimensions. So then a good sort of setting would be like this, that for every point of our configuration, there will be an algebra for every, let me call them I, point in I, or a DG algebra, associative algebra. Let's call it SI. differential graded. So for instance, if just a base field, it's okay. Yeah? For every pair of indices, it may or may not be commutative, but we don't require this. A bimodule, Nij. So bimodule over Si, left over Si, right over Sj. Such that Nji, so we'll assume this is a projective over the tensor product, Si tensor Sj op. So just if you forget the differential, so it's something that we can always do this up to homotopy, just for simplicity. Okay? And I want to assume self-duality in the following form. Nji equals Nij star, but I have to explain what it is Nij star. It will be Hom. Well, we can say Hom over this dual over this space, over Si tensor Sj op, from Nij to Si tensor Sj op. Then, so this will be a system of coefficients. Then for every subpolygon, we have, say, Q prime. Q prime on vertices in our set. We can form, let's say, Q prime, A prime. A prime as the set of vertices. Well, and we can form the cyclic tensor product. And Q prime, well, let me first write it, cyclic tensor product, which means that we have vertices over the polygon going around the circle, say I0, I1, I2, In. So we tensor multiply this bimodal with this bimodal over this ring, and this bimodal with this bimodal over this ring, and we can go all the way together, so they're sort of holding hands together, and the result would be just a vector space. So let me draw this picture here. Cyclic tensor product.
If they were kind of alternation, yeah, then you don't need self-duality, sorry, right?
Yes. Yes, so this is somehow set up in a symmetric way. Yes. So we just write N I0, I1 tensor over S I1, and I1, I2 will be tensor over S I2 and I2, I3, and we can, in principle, we can go all the way around. So then, if a polygon is subdivided into a bunch of other polygons, then maybe I'll draw this here. So if a subpolytope Q prime is subdivided into some Q second nu, let me just consider a case of subdivision into maybe something like this. So then we read this one counterclockwise, and we read this one counterclockwise. So, and this edge here, for instance, this is I and J. So here in the tensor product, there will be Nij, and here will be Nji. Yeah, and we pair them together using this pairing appropriately. So we get a map gamma from tensor product of Nq prime nu to Nq prime. And this is sort of associative in the sense that if we subdivide further, it will be composable. So in this way, what we get a system of sheaves, which are on each secondary polytope. We have a cellular sheaf, a sheaf which is constant on every face. But some vector spaces, those vector spaces are associated to faces. And the system of those sheaves will be factorizable, again, in that sense. So let me maybe do this here. Let me do it here.
This picture forces that you on dimension 2?
Well, so it doesn't. In order to get to higher dimensions, we should speak not about Lie algebras or associative algebras, but should speak about appropriate structure of E and ED algebras. So this is a natural context here. Maybe at the end I'll say a few words. So how much time do I still have? So we have those maps, those generalization maps, and they give, so this gamma, the gammas give rise to a factorizing system of sheaves on the sigma of A prime. Which means that if I have a face of this secondary polytope, it's a product, and the restriction of the corresponding sheaf to this face would be the external tensor product of those sheaves. And this, again, by the same formalism, give rise to G. An algebra which now will depend on this data. Let me call this data just by one n. It's called Gn. Will be direct sum over A prime. Here I simply say n A prime, tensor or sigma of A prime. So this is a complex, right? Minus dim sigma of A prime minus 1. Again, is a nilpotent L infinity algebra. So now, let me explain the motivation for considering this in the which uses this those words of algebra of the infrared. Yes, I should probably say this too. Yes, yes. So this is a Lie algebra, this Lie infinity algebra, and so inside will be G and geometric. It will be direct sum, not over those sets, but over subpolygons. And here I write n of A intersected with Q prime. This is the way to simplify this algebra, to remove the freedom of considering several choices of points inside one polygon. So it's a sub-Lie infinity algebra. Sub-algebra. So let me say this part. Yes, it has trivial differential. No, it's not exactly, because if there's differential here, then it sort of percolates. Motivation will be in the algebra of the infrared of the Morgenritter. So first of all, why infrared in the first place? So from general physical understanding, the infrared analysis correspond to study the vacuum or different vacua. So infrared sort of equals to collection of vacua plus instantons tunneling between different vacua, and plus sort of perturbation in this direction. Instantons tunneling between them. So, and in particular, so this is a kind of general physical principles. We are interested in what's called as Landau-Ginzburg model, which simply means for us that we have a Keller manifold X, and we have a holomorphic function on this, call it W. So the manifold is not compact. It's holomorphic. Let's assume it's a Morse function. Holomorphic. So then it's a Keller manifold. It has a Keller form omega 1, 1, which is as well known as a Riemannian metric plus I times symplexic metric. So, and the set A would be the set of W of XA is the set of critical values. So it's a subset of complex numbers. So we mark it on the plane. So some of them lie inside the convex hull of others. So W is a Morse function, a holomorphic Morse function. So the real part of W equals real Morse function.
But you don't assume well being proper in some sense, compact fiber work. No?
Not necessarily. We can assume it, yeah, but it's not. So it can be just.
The real category usually it's assumed.
Huh?
The real category.
Yes. Yes, but we consider sort of more, in a way, more formal study of this. So, and we look at gradient flow. Gradient flow. And this is well known as the same as Hamiltonian flow. Hamiltonian flow for imaginary part of W. And the Hamiltonian is preserved, so it means that the images of the gradient flow lines would be half lines like this. So typically, if they all have different imaginary parts, so they could never intersect. But if we rotate it so that they become on the same horizontal line, there may be some non-trivial intersection. Let me do it here. So let's write it like this. So for every I and j, so I and j would be points here. So look at the rotated function e to the theta ijw. Theta ij will be this angle. And we'll look at nij to be the number of gradient trajectories of a real part of this, which goes from I to j. So they will project into straight intervals. So gradient trajectory. Of real. Yes, appropriate number, yes. No, actually, no. I just want, let's say the number, and then make a vector space out of them. Okay, e to the theta ijw from critical point xi to critical point xj. And let big Nij equals space spanned by them with appropriate grading and Floer type differential. Space spanned by them. Yes, the ugal, yeah. The angle, yeah. Yeah, so then this gives rise to a system of coefficients n, which corresponds to all algebras being the field, and those Nij. So in principle, one can imagine a more general situation when this is not necessarily a Morse function. So singularities are not necessarily Morse, not necessarily isolated. In this case, those would correspond to the Fukaya-Seidel categories of those local singularities. And this would be certain by models, which also, in principle, one can imagine such a construction. I'm not sure, probably this construction has not yet been fully developed in symplectic topology. But anyway, so algebraically, one can imagine this setting. This is the motivation, and we want to study this Lie algebra. So Lie algebra corresponding to this setting is particularly interesting from physical point of view. So corresponding G is important. Okay, so.
That G will be an L-infinity algebra.
Yes, it will be an L-infinity algebra. So now it's actually important in this case that for in 2 dimensions we can, and actually in any number of dimensions, we can consider the relative setting. Which means one point at infinity. At infinity. And this actually putting one point of infinity is exactly the setting when Fukai's ideal category is defined in symplectic topology, which has put this move of everything into one direction. But we can consider formally the setting. We can consider that our set A has one extra point, which can be either actually at the projective infinity or simply far away, something like this. So we can have a new set, say A tilde, which is all set A, together with one point infinity, which is outside of everything. Then in this case, we can form the corresponding Lie infinity algebra, call it G tilde. We can do it with coefficients. We can do it without coefficients. And it has, so first of all, it has an ideal, in the obvious sense, ideal called G infinity, which consists of infinite polygons. Polygons of which one vertex is at infinity. Equal span of, well, I use this notation VA for the generators. I can say it again, sorry, or VQ prime for Q prime contain infinity. And the subalgebra, sub-Lie infinity algebra, G F, which is simply the algebra corresponding to this A. So G A. And this is a direct sum of both of them. So which means there is a canonical map, say alpha, from GF to, so when we have an algebra, Lie algebra G hat, which is a direct sum of a subalgebra and an ideal, it means that the subalgebra acts on the ideal. So, and in the L infinity situation, we will have sort of derived action. I write derived functor of derivations of G infinity. So, so this is Lie algebra.
The differential, have I got this right? The differential preserves GF, but it doesn't preserve G infinity?
It preserves, the G infinity is an ideal, so it preserves even in more, in a bigger sense.
Well, yeah, but I don't see that because I could imagine having convex subsets that don't include infinity.
Well,
Maybe I've lost track.
no, if you have something which is finite and something is the infinite, the result will be infinite.
Yeah.
It's ideal.
Yeah. Yeah, yeah. So in this way, yeah. So it's a derived derivations. In particular, a Maurer-Cartan element here, so Maurer-Cartan, give deformations of G infinity. So, but in dimension 2, so this can be done in any number of dimensions. But in dimension 2, this infinite part is really near infinity. The situation is somehow has one dimension less, and everything is ordered. Oops, I'm sorry. And everything is ordered. So, in and D equals 2 situation near infinity is one dimension. So everything is ordered. So G infinity can be lifted from a homotopy Lie algebra to a homotopy associative algebra. Let's call it A infinity algebra. by the so algebra from which, by the analog of the formula, the bracket is AB minus BA. And let's call this algebra R, and it has an upper triangular structure, because what happens here is just we can combine them in the order. So it has upper triangular. R is upper triangular. Or using the more derived category language, the category of R modules has a semi-orthogonal decomposition. And we have a map. We can extend this to homomorphism psi from G to the Hochschild complex of R. So it's a Hochschild. Which, again, is well known, governs deformations. GF, yes, GF, yeah. So in fact, if we work with coefficients, then we'll get the image, not the entire Hochschild complex, but a subcomplex which governs deformations that preserve this structure, that preserve semi-orthogonal decomposition. So let me just do one more permutation here. And then I'm almost done. So this psi takes values. Let's call the or in the subcomplex. Let's call it Hochschild with the arrow, which is, let's write something like this, is the most natural thing that writes itself, would be something like this, over I0 less than I1 less than IN. And less than means in the sense of that order upstairs. So we have hom over Si0 star tensor Sin. Here I have R I0 I1. So this refers to this triangular structure, tensor Si1 R I1 I2 tensor R In minus 1 In over Sin minus 1. And then in this complex, and then what we can prove is a certain universality theorem, that this algebra GF is the corresponding morphism is a quasi-isomorphism, called the universality theorem.
Sorry, home to what? You left out.
Home to, yes, to R I0 IN. So we think of this now as a sort of category with semi-orthogonal decomposition, yes, and we try to deform it in a way that would preserve this thing, so that's what we write. Universality theorem. That the L infinity morphism, this will be an L infinity morphism, called psi from GF to ordered Hochschild complex of R is a quasi-isomorphism. It means that every deformation of any semi-orthogonal deformation comes from a Maurer-Cartan element, i.e. any deformation preserving semi-orthogonal structure comes from a Maurer-Cartan element in G finite. And then the somehow physical motivation of Guyot, Amour, and Witten was to give particular examples of such elements which would recover the Foucault-Seidel category. So let's try to go more width and goal. So, and here in principle, there may be several approaches. We're still thinking on other approaches to this problem to find the Maurer-Cartan element, let's say gamma, find gamma recovering the Foucault-Seidel category. Of W. So anyway, so this gives a certain class of Lie algebraic structures just coming from basically from nothing, from secondary polytopes, and there are interesting relations with Hochschild complexes, and in higher number of dimensions, this should be understood in terms of ED and ED-1 algebras.
I think so. Swiss cheese also.
Yes, Swiss cheese. So this is sort of by now a classical area of thinking. So how we think of deformations of EN algebras. So this is a version of the Lie conjecture. But anyway, so the structure itself is completely elementary, and this is what I wanted to present today. Thank you very much.
Questions? Is this supposed to work in the case when you have Landau-Ginzburg model with non-isolated singularity?
Well, so this setting is sort of designed to work with this whenever the symplectic people will construct corresponding categories.
So how do you see a thimble in this language?
Well, a thimble is exactly so those lines are intersections of symbols. So a gradient line from one critical point to another.
But what if they are not isolated?
No, that I don't know.
I have a map from something. So one global homology French itself. One homology.
Yeah, you can categorify. Actually, that was their goal. They wanted to categorify 2D wall crossing.
So in your construction of G, you neglected those sets of vertices which didn't span.
Yes.
Is there any way that any of them might have a role, do you think? To give some negative...
In principle, yes, but I don't know.
Yeah, I asked physicists about that, they didn't know.
Yeah, so maybe, so it may... Yes, I agree. It's a little annoying that we disregard them. It would be better to not have to disregard them, but to do something.
So we all have the same reaction, but without knowing what we're meant to be, what physics we're meant to be doing. Okay.
What questions?
In the case where on a face you could factorize the polynomial, so typically in singularities you have a face which is a line, and in the middle of this face some element, such that the whole face polynomial becomes square. Then you run in trouble. So in the case the Milnor number goes then drastically up.
Here I'm talking about a secondary polytope, but not of the set of monomials at all.
Yeah, but I'm still allowed to think that alphas are integral value, or integers.
Yes.
So then I can take polynomial with two p subpairs.
No, but we don't do this at all, because those W's are not monomials. They're critical values. Yes, they're complex numbers.
Not what think we should